right, welcome everybody. So, how many of you heard of runtime verification? I'm curious. All right. Okay, so Runtime Verification is a technology company specialized in proof generation and verification. And our core technology is the K framework, which enables general purpose and versatile tools and solutions for the development of products and infrastructures that are secure, scalable, and efficient. We are probably known mostly as security auditors with emphasis on formal methods and formal verification. We were the first company who brought actually formal verification in the blockchain space. We formally verified the first version of Uniswap and the Ethereum 2 deposit contract. So the first specification of ERC20 was also written by us in the K framework. However, what I'd like to convey in this presentation is that we are more than security auditors. So we develop technology that can be used for security audits as well, but it's a lot more general and powerful than that. And I'd like to give you a glimpse, first of all, of the technology that we have, and then where we'd like to go. So it will be a bit of a visionary presentation. What I'm not going to talk about is all the audits that we've done, all the companies that we made happy. You can find it on the internet. So let me jump directly to the end, to the vision, what we'd like to achieve. So we'd like to create a framework that extends our existing technology into what we want to call universal truth framework. So what is that? It sounds very abstract, I'm sure. It's a framework in which any claim that is made in the framework is verifiably true. Don't have to trust who made the claim. You don't have to trust even the claim itself, because you can check it. And how is that done? Well, the claims will come with independent and succinct certificates, which are third-party checkable. So if runtime verification makes a claim and says, hey, this token is a correct ERC20 implementation, you don't have to trust us. You have to just take it and check it yourself. And now what is a claim? Because it sounds very abstract, right? So a claim can literally be almost anything that is computable, anything that can be produced by a program or by a tool that analyzes a program or improves something about a program. A program execution, for example, that's a claim. Right? When you execute f of 17 and you get 42, that's a claim that f of 17 is 42. When you say that this token is an ERC20, that's a claim. When you say that this program, this smart contract is secure, that's a claim. Right? So all these claims, when you say that Fermat's theorem holds, so mathematical theorem, that's a claim as well. Right? So all these claims in this universal truth framework are going to come with proofs that can be checked independently and efficiently. And the proofs will be very small, succinct. Okay, so that's the vision. That's where we want to take all this technology to. Feel free to interrupt, ask questions along the way. I'm happy to take them. Any questions so far? Is this crystal clear? All the details are clear, right? Okay, bon. I mean, the ultimate effect is going to be that you as a user take a claim and a certificate for it produced by the framework, this PI, check it yourself with a verified checker, and now you know for sure that phi holds. Okay, there is no doubt. It's the best mathematics can do. Okay, for us, that's there. That's the idea. And you can do a lot of things with this. This already generalizes a lot of existing technologies, like verifiable computing, for example, is captured by this picture. Everything, almost everything you can do with ZK technology is captured by this. And more. I'll give you more examples. Let me give you a glimpse of how this can be realized. The K framework, I told you it's our core technology. You don't have to know what it does. Just think about it as something very smart, some sort of AI, some smart brain, or smart human even, that takes a claim and proves it mathematically in the standard sense. Okay? And a mathematical proof in the standard sense, when you go to the last level of details in the proof, is huge. Right? So imagine like you have a huge mathematical proof, Wi-Fi is correct. And K is a framework and with a suite of tools that help you find these proofs, mathematical proofs. Okay? Is this enough? You can say, hey, use K and that's it, you got your proof. What's the problem so far? This is huge, can be like terabytes of steps, right? And you want to make a claim that phi holds, and you want to send it around to everybody, to all the nodes on a blockchain, for example, to validate a transaction. You cannot send these huge proofs, right? So you need to compress them, to make them succinct. And this is where we combine what we have so far in the K framework, we combine it with a SNARKed proof checker. So the advantage of having all the details in a proof is that you can check the proof with a very dumb, very simple, very trivial proof checker. Okay, so that's good. It's good that you have a very small proof checker because this is the only part of the whole picture which needs to be trusted. Everything else is checkable. K doesn't have to be trusted anymore. K will produce a big proof, which I can check. Yes, it can check the proof, but why should you trust that if it tells you true, it's done? You want to check the proof locally, you don't want to ship it around. So that's why we need to snark this, to generate a circuit for this and snark it, and then generate a succinct, small, hopefully fixed size, 256 bits or so, certificate that attests the correctness of the claim. Okay, so that's the big picture. Use K to first get a big mathematical proof, and then snark it, make it a very succinct argument, cryptographic proof. And now you can engineer this. You may not want to generate all that proof. Actually, that proof can be so large that you cannot even store it. Right? So you may need to pipe it with a proof checker, right? So you never store it. Right, so that's the high-level idea. And I told you that it captures all the existing uses of ZK or verifiable computing, but it also enables a completely new, and I'm tempted to say crazy, but it's not crazy at all, actually, idea. You can have a blockchain of truths, of facts that are checked and hold for sure. Okay? And that blockchain would allow you to write arbitrary claims, stored, checked, executions, correctness. For example, if we audit a protocol, we don't have to generate a PDF anymore. We can put a cryptographic certificate on the blockchain that that smart contract is correct with respect to a certain specification. It's a correct implementation of ERC20. You saw the ERC-X tool. They can generate a certificate, and then that certificate can go on the blockchain, and that's the argument why that is correct. Also, you execute transactions only once and for all. You never have to re-execute them. And you know that every single claim on this blockchain is going to be true because it has been mathematically derived and then it has been checked by a proof checker. So we have a cryptographic proof of a mathematical proof that exists for the claim. So it's a proof of proof, if you want. All right, so that's an application which I don't think is too far away in the future. Let me tell you briefly what K is and why we created it. So in the programming language field, we have lots of programming languages and lots of tools for them. And all these tools are useful for execution, for analysis, for formal verification. We have uses for all these tools. But the problem is that there are too many combinations of languages and tools. For example, let's see here, Ethereum interpreter. That's the EVM, an EVM interpreter. Okay? Then you have a C compiler. GCC is this arrow from C to compiler, right? So all these arrows are like huge, big systems by themselves. But that's how we do things in the programming language field. So there are lots of them, lots of languages, lots of tools. And these come with pain points for developers, pain points for users. For developers, we have a lot of duplication of code, of effort, and the same tools implemented over and over again for different languages, and so on and so forth. So wasted talent, it's error-prone, tools out of sync with the actual languages, and so on. On the other side of the users, us, we have to accept, to trust a lot. We have to trust the compiler of Java. We have to trust the compiler of Solidity. We have to trust all these things. A huge complexity. So that's what K tried to address from the very beginning. Actually, I proposed K back in 2003, but the ideas are older. We started thinking about these ideas back in 2000, 2001, while at NASA. So anyway, so this is how K addresses the problem for the developers. It basically separates completely languages from tools. So all the tools are implemented in a language agnostic way, or language parametric way. And there is a language of K, a meta language, that allows you to define languages in it. Okay? So you define every language that you want to support, and then plug it into the framework. So plug and play your language and you get your tool. So if you want a symbolic execution engine for C, take the semantics of C, plug it into the symbolic execution, and you got a symbolic execution engine for C. If you want to program verifier for EVM, take EVM, plug it, get the deductive verifier. So that's for developers. So now you don't have to maintain n times m arrows, but only n plus m, and completely separate and independent from each other. For users, remember the problem with users was that users had to trust all these things. Well, so in K, everything that happens, everything that K does, even parsing, everything can be explained as a mathematical proof. And in logic, we write proofs like this. So it says in a mathematical theory, a certain task holds, a certain theorem holds. So everything is a proof. Even an execution of a program. When I execute the program, I told you f of 17 is 42, that's a mathematical proof of a theorem, that f of 17 is 42. Right, so computations are special cases of proofs. And this is something that we found that many people have a hard time to grasp. It's a lot easier to grasp the fact that this token is a correct ERC20 implementation, that is a theorem, and it's a mathematical proof, than to say that an execution of a program is a proof for a theorem. But yeah, in the K framework, they are the same, just a mathematical proof. And I told you that there is this proof checker that we snarked. So this proof checker is disarmingly simple and small. There's only 240 lines of code. Okay, so 240 lines of code that allow you to check any property about any program in any programming language. And that's the only thing that you have to trust. All right? Yes? That's a good way to look at it, definitely. Yep. But it's not a translator, it's a creator. It allows you to create these mathematical artifacts for the things that are very intuitive in your mind only. If you define it in K, for example, the logic of Coq, we defined that in K. And now you can take Coq proofs and regard them as proofs in this logic. Exactly. And then you get a very small, succinct certificate. This is true. This is true. What is that? It's like a shortcut, yeah, for the whole thing. But the whole thing can be huge. You know, that's what mathematicians did for 5,000 years. They proved theorems, and they are huge. Yes, but the challenge here was to find that particular formalism in which you can reduce everything to 240 lines of code. All right, cool. So that's K at a high level. What is new in K? Those of you who knew K, now we'll see some new things. So we have a K summarizer, which is at the core of various of the tools in K. I told you that K is a framework that allows you to develop tools on top of it, which are general, scalable, and so on. So there are lots of components that we put together in order to build these tools. But this is one of them, one of the most important ones, which, given a programming language, here we just use EVM, but it can be C as well. Let's take EVM, and let's take this contract. What does this contract do? Not a very funny one. Just calculate the sum of numbers from 1 to n. Can you spot a problem actually in this program? If the input is 0, what do we get? 1, okay, which is incorrect. Okay, so that's telling us that the users of this smart contract expect this function to be called with arguments larger than 1. Okay, but we don't know yet that. We just have code here. Right, so what the key summarizer does, takes such a program in a programming language, and the key summarizer doesn't know anything about any programming language, right? So it takes a programming language as input, takes a program, and then it generates something like this, which in compiler theory looks like a control flow graph, but what it really is it is a control flow graph, but it is derived completely automatically from the program and the programming language, correct by construction. So you have a mathematical proof that this is correct. It captures all the behaviors of that program. Okay? And now you can imagine that you can do lots of things with this. You can prove properties about the program. You can actually execute the program a lot more efficiently because you can run this and so on and so forth. Many tools build on this. Yes? Nope. It extracts the behavior from the contract using the semantics of the programming language. It already knows the meaning of the programming language. It already knows the meaning of every single language construct. So why give it? You can extract it. Well, so this is saying anything about correctness. Actually, this program, as a matter of fact, is wrong. Right? Because it's summarizing the behavior, yes. And now if you want to prove it correct, you need other properties that you want to prove, and you'll prove them here instead of there, because this will be a lot faster, orders of magnitude faster than there, because I don't have to redo work. Okay? Actually, one of the tools that you guys use at Blockswap, and it helps with the correctness of the gateway, is the case summarizer, is the Foundry, the K-Foundry tool. How many people here use Foundry or heard of Foundry? Okay, cool. Right, so in Foundry, you write parametric properties, property tests, right? And then you can generate random tests, fuzzy tests. Okay, thousands of them, tens of thousands of them. Pushing a button in the tool, right? So what we offer here is another button. You don't have to change anything in the properties, in the way you write the test. But when you push the other button, prove, instead of running random tests, instead of fuzzing, you actually prove those properties. It will consider those properties as specifications. It will try to prove them. Okay, for our contract sum, you write a test like this in Foundry. Let's see if I can use the mouse. Right, so you write a test like this. You see n is the parameter of the test. And you say n is large, and now you can assume and assert things. You assume n is larger than 0, then you run your code, and then you assert that the result should be this thing, which is the sum of numbers up to n. Notice that I said n larger than or equal to 0, right? We know that that is incorrect. However, Foundry is not able to find it. We're just generating random tests. Because the state space of the input is infinite, anything larger than or equal to 0 can be generated, it will not find it. If you assume more, if you can restrict, if you range the input up to 10, it will find it because it generates exhaustively all the inputs. But you don't know in real life. This is a super simple example. You know how to range the inputs. Okay, but if you push the other button, prove, it will prove it. Actually, not it will prove it, it will tell you that this is not correct. It will find a counterexample for you. Okay? So the reason we like to incorporate K in such kind of tools is because developers are already used to writing such properties, and the learning curve is 0, basically. That's a big problem with formal methods, learning curve. One thing that is not super known, and sometimes is misunderstood, is that parametric tests, or property tests, like in Foundry, are almost as powerful as formal verification in general in terms of expressiveness. Okay, so those of you who are familiar with formal verification, you know that the way to specify properties is to use the so-called Hort triples or correctness triples. We have preconditions, postconditions, and code. and all these may have some free variables ranging across all of them. And it is a very simple and direct way to translate those correctness or specifications in formal verification to properties like this. You see, I just assume, I take all the variables as parameters, I assume the precondition, execute the code, set the postcondition. Okay? So if Foundry was smart enough to prove that test property, you would get exactly the same result as a formal verification tool would get, when verifying that correctness argument. My point here is that a tool like Foundry is powerful enough to allow you to do full-fledged formal verification. You may need to add little things here and there, and you can do it through cheat codes, but I'm not going to go into those details. And for our example, that's how the property looks like, and the key prover will prove it for you. All right, any questions so far? All right, you already saw this. Sometimes you already know the specifications, you already know the properties, and when you know them, then you can run them against lots and lots and lots and lots of programs, and that's what the ERCX tool does that Matt and Vince already mentioned. Okay, so you just pass your address here, and it will run it and check it and everything for you. Yes? Yeah. And it will do everything I showed. It will generate that summary and so on. Okay? It will spit out which tests fail, because we have a bunch of tests, I don't know how many, like 60, 70 in total, something like that. And some of them may hold, some of them may not. And actually, based on those, who can characterize what kind of ERC20 token you have, because there are 20 plus different categories of ERC20s. But what I'm trying to get to is how you can build all these tools from basic components that the K framework provides. So K gives you the full capability to prove anything you want if you put the effort into it, but if you limit its capabilities, if you reduce it to something very domain-specific like this, then you can automate it almost completely. And this is not important at all for this crowd here, I'm sure, but we can do exactly the same thing with C. It doesn't have to be EVM or anything. As a matter of fact, we have a tool called RV-Match, which is K instantiated with C, and we use it actually right now to formally verify a Solana validator for Jump crypto. All right, as you may expect, K is a huge system. We heard many people saying that this is most likely the largest formal methods system ever implemented. It has more than 500,000 lines of code in 4 different languages. And you may wonder, why should we trust K? And my answer would be, you shouldn't, because K has bugs, I'm pretty sure. I'm convinced it has bugs. We fix them as soon as we find them, but it has bugs, any system has bugs. All smart contracts we verified, even if they had like only 500 lines of code, we found bugs in them. So almost everything has bugs. The question is how to deal with them. And I told you our approach to deal with them is not trust K, but force K generate a proof of what it did, and then check that proof, which is a lot simpler to check. Okay? And if the proof doesn't check, even if the fact is true, it's still rejected. Okay? You have to be able to generate a proof in order to be trusted. All right, so now we get to the hairy part. Yes? The proof is either valid or with the no. Actually, no, it's not. You are right, it's not. But the fact that the proof is not can mean that the K tool was not able to generate it. Because it's pretty tricky to reverse engineer all the optimizations we've done in K in order to generate a proof. Part, yes, exactly. But the nice thing is that you can hack that as much as you want. It doesn't matter anymore. It doesn't have to be correct. As far as you can produce something correct, it's good. Okay? Because many people try to prove compilers correct. That's a huge effort. It's a 50-man-year effort. 50 PhD man-year effort, right, to prove a compiler correct. It's super hard. Why? When you can take each program and prove that that program that was compiled is correctly compiled based on the semantics. And that's a lot simpler to do. This is called translation validation, by the way. All right. So what is that logic, fundamental logic that allows you to express, right, all these properties, claims, and proofs in it? And this is the result of 30 plus years of work. Okay? It's so hard to do simple things. Right? It takes a lot. Basically, that's the whole logic. You can write it on a napkin. You can even have, once you get it, once you understand it, you can even have 6 beers and then still write it on a napkin. It is very intuitive, very clear. Of course, I cannot go through it, but the point is that it has 15 proof rules, and the proof checker only has 15 cases, right? And checks, are you in this case, are you in this case, are you in this case? Like modus ponens, right? That's one of the proof rules, right? It checks every single one. And what's, again, important is that this logic allows you to define any programming language. And any claim, like ERC20, is a specification in this logic, or such a phi, such a formula phi. And this is more general than K, right? So K is a best effort. It's just a heuristic, helps you find proofs. But you can use Coq instead, or Lean, or any of these interactive theorem provers, right, to get proofs. And then once you have the proofs in those, there is a mechanism to desugar them, to translate them to proofs in matching logic. My point is that you can use the same backend proof checker for all these formalisms. Of course, we are working with K, but it's important to know that this is more general than just K. But all these tools, all they do, they reduce claims to mathematical facts like this. In this theory, gamma, this claim phi holds. And then you have a sequence of steps, millions, billions of steps that derive that theorem. Okay? So, and this is just a logic, it's a paper, napkin, okay, definition. How to implement it? You can implement it in any language you want, right? But we chose MetaMath as a language to implement it. Why? Because MetaMath is a super simple language, so simple that you can implement it in a morning. There are more than 20 implementations already available, several on FPGAs, on hardware. And I think only one of them is larger than 1,000 lines, has like 1,500 lines of code. But all the other implementations of MetaMath are a few hundred lines of code. So MetaMath itself is super simple. And then we implemented matching logic in MetaMath in 240 lines of MetaMath. This is a snippet of the definition. Okay, axiom, this is a proof rule, it's a modus ponens rule. Right? So basically, MetaMath allows you to implement logics. And then, once you have the definition, now I can take any proof. This is what K spits out. This is a mathematical proof in K, which 44, but it can have like millions of steps. Right? And then MetaMath will check the proof for you. So 240 lines of code in a language which has lots of implementations, so you can run this in all these implementations in 200 lines of code as well. Okay, compare that to other tools like Coq or Lean, which have like thousands of lines of code, proof checkers implemented in high-level languages like OCaml, which then are compiled with complex compilers to LLVM, which are then translated to native code, right? So it's a lot of trust that you have to put in those, while here it's minimal. All right, so let me wrap up. So what we are proposing here as a universal truth framework is a framework in which you have tools like those generated or provided or built using the K infrastructure that take input from users or from the blockchain. For example, the definition of Ethereum, of EVM, that should be on the blockchain somewhere. The fact that it is not is crazy. It should be on the blockchain and everybody should agree on it. And that should be vetted by the Ethereum Foundation or some authority. Okay? Then, so it takes as input all these different things, and then it generates, for any claim that is checked, it generates a proof, a succinct proof, and that succinct proof can be checked by anybody, by any third party, and that's all the third party should need in order to be absolutely sure that the claim holds. Okay? So everything I presented here is also what you use under the hood when we do audits, when we do code review, when we do business logic, specifications, and so on. But what's important to know is that all these converge, all these lead somewhere. This is the vision, this is where we want to get. And it may take a few years, but we'll get there. And I hope that maybe we can use some of this also with a gateway, because K in particular is multi-chain, is multi-language. And you can have these proofs from one chain, produced by one chain, sent to the other chain. And it looks like a natural fit with what you guys do. Yes? So in words, a claim looks like the bytecode of this address is a correct implementation of this ERC20 token specification. Or also in words, can be like sum of 10 evaluates to 55. Okay? That's also a claim. But you have to write it in MetaMath, right? It's a very strict language. And you have to make sure that you write everything perfectly, no extra spaces, no anything, because the proof checker, remember, is very dumb. Doesn't want to parse for you. Completely language dependent, right? Everything that K does, all those tools, blue tools, language dependent. But when you build tools for a language like the K Foundry, that becomes language dependent. But that's fun, actually. Now you want to do something for a particular language, but use the infrastructure, which is completely language independent, to plug and play your language. Is much more? It depends on the context, I guess. It can be harder. Many people who use K, raw K, they find it difficult to use. That's why we try to develop these tools that are basically really user interfaces to make things easy for users. But it's good to know that under the hood, everything is super rigorous. And if we generate these certificates under the hood, you have a nice user-friendly user interface, like the ERCX website, push the button, wait, get a certificate. But this is my token, it's correct. Yeah? Yeah, everywhere. Yeah, completely elsewhere, yeah. Actually, you want to prove it elsewhere because this is very intensive to do a proof. It's a very intensive process. But once you get a certificate, then you can deploy it on a blockchain. I think the future blockchains will not even have virtual machines. Why run a virtual machine in a node? We run virtual machines just because we don't trust the other nodes, right? But if we know for sure that the thing holds, then we just deploy the claim. Yep. I think, I don't know. All right, thank you.